CQ. This is Victor Uniform 3. What if your antenna is secretly destroying your radio's performance every single time you transmit? A bad antenna match can reduce your signal range, create massive reflected power, overheat your transmitter, and in extreme cases, even damage your expensive RF final amplifiers. And the scary part, most of the operators never realize is happening. That's why every ham radio operator, beginner to an expert, needs a SWR meter. Today, I'll show you how to make your own SWR meter completely from scratch. No expensive lab equipment, no complicated circuits, and it works for HF, VHF and even UHF frequencies. By the end of this video, you will learn how to build this SWR meter completely from scratch. So grab your soldering iron, let's build something unique. Before building, we have to understand working principle of the SWR meter. This SWR meter uses a directional RF bridge to measure forward and reflected power separately. The center track is the main transmission line. It connects the transmitter to the antenna, and all the RF power flows through this line. Above and below the transmission line, there is two additional tracks called pickup lines. These pickup lines are not directly connected to the RF path. Instead, they pick up a very small amount of RF energy through electromagnetic coupling from the transmission line. The lower pickup line is designed to sample the forward traveling RF wave. So, when the RF power moves from the transmitter towards the antenna, this line picks up the forward RF signal. The upper pickup line is designed in the opposite direction. So, it mainly detects the reflected RF wave coming back from the antenna towards the transmitter. The 100 ohm resistor connected to the pickup lines act as a termination resistors. They absorb unwanted RF energy and help to improve directional accuracy. The sampled RF signals are still high frequency AC signals, so they cannot directly drive the analog meter. That is why Schottky diodes are used. The diodes rectify the RF signals and convert them into DC voltage. The capacitors connected after the diodes act as a filter capacitors. They smooth the detected DC voltage and prevent the meter needle from fluctuating rapidly. An SPDT toggle switch is used to select either the forward signal or the reflected signal and send into the single analog meter. The 10K potentiometer is used for calibration. In forward mode, the potentiometer adjusts the meter sensitivity into calibration point. After the calibration, switching to the reverse mode shows the reflected power level. This is how the SWR bridge separately measures forward and reflected RF power using directional coupling. Now, let's build the most important part of this project, the directional coupler. First, print the directional coupler layout using a laser printer onto glossy paper. The black toner will act as a etching mask. The layout contains the main 50 ohm RF transmission line, the coupled sensing line, and the detector connection pads. Next, clean the copper clad board using a steel wool. Any dirt or oxidation can prevent the toner from sticking properly. Now, place the printed artwork face down onto the copper board. Using a hot iron, apply firm pressure evenly for several minutes. The heat transfers the toner directly onto the copper surface. This process is almost identical to making a homemade PCB for electronics projects. After cooling the board in water, gently peel away the paper. You should now see the RF coupler traces transferred onto the copper side. Fill the cracks using a permanent marker on the transferred mask. Next, place the copper clad board on plastic tray. Etch the board using ferric chloride or another PCB etching solution. Shake the plastic tray for faster etching process. After etching, the exposed copper dissolves away, leaving only the RF transmission line and the coupler traces. After etching, wash the board using water. Using the acetone-based thinner, you can remove the toner from the PCB. The acetone-based thinner dissolves the toner from the PCB, so we can easily remove the toner from the PCB using a cotton cloth. Notice how short and clean the RF traces are. That's why PCB construction works so well for making SWR directional couplers. Finally, drill the mounting holes for BNC connectors. Now the drilling process is completed. Now the BNC connector is perfectly fitting on the PCB. I made an enclosure for the SWR meter using the PVC sheet. Drill holes on PVC sheet for mounting BNC connector. Using a step drill bit, we can make suitable hole for fixing BNC connector. Now let's connect the BNC connector on PVC sheet enclosure cap. After fixing the BNC connector, mount the directional coupler PCB onto the BNC connector. Now solder the BNC connector onto the directional coupler PCB. Now the soldering process is completed. Next, connect the required components on the directional coupler PCB. Now the directional coupler PCB soldering is completed. For the meter movement, I am using 100 microampere moving coil meter I salvaged from old analog multimeter. Fix the moving coil meter onto enclosure box using glue. Also connect the calibration potentiometer and SPDT switch onto the enclosure and connect all the wires according to the circuit diagram. I just made a wiring mistake onto the calibration potentiometer side. Connect the calibration potentiometer according to this new circuit. Now let's connect ground forward and reflected wires to the directional coupler. Now we can close the enclosure box. After closing the enclosure box, we can add the labels for SWR meter. The making procedure of SWR meter is completed. For testing the SWR meter, I am using my homebrewed modular BitX40 SSB transceiver. I assembled this SSB transceiver module by module, so I can easily understand how the BitX40 SSB transceiver works. For boosting the power level, I am using my homemade 50 watts RF linear amplifier. If you want a video about how I made this thing, please let me know in the comments. Now I connected my transceiver, power amplifier and SWR meter. For HF SWR testing, I am using my homemade dummy load instead of external antenna. I will show you what's inside the dummy load. I connected 2 watts 21 kilo ohms resistors in parallel to make 50 ohms dummy load. It's time to calibrate the SWR meter. Set the switch in forward mode. Press the PTT button and blow to the mic. Adjust the calibration control until the meter reaches the maximum on the scale. After reaching maximum on the scale, set the switch to reverse mode. Now you can see with the perfect dummy load, the reflected reading is extremely low. I am going to remove the dummy load. You can see without load, the SWR reading is extremely high. Again connecting the dummy load, the SWR reading is now very low. This is the nano VNA SWR reading of my homebrewed external inverted V antenna. It's showing low SWR at 7 MHz frequency. Next, remove the dummy load and connect external inverted V dipole antenna. After that, set 7 MHz frequency on transceiver. Now repeat the same SWR testing process. You can see at 7 MHz the meter is indicating very low SWR value. Now I am going to increase the frequency and again repeat the SWR testing process. Now you can see at a high frequency the SWR is little bit high as shown in the nano VNA. Now our SWR meter HF testing is finished. For VHF and UHF testing, I am using my homemade dual band Moxon Yagi antenna because I don't have VHF UHF RF grade dummy load. Now I am connected the transceiver and Yagi antenna to SWR meter. This SWR meter very sensitive to VHF and UHF frequencies. Now I am checking SWR on 146 MHz 2 meter band. Now you can see a very low SWR value on 2 meter band.
14500.
On 145 MHz, the SWR values is little bit high. Next, I am going to test SWR on UHF band.
4 3 6 0 0.
You can also see the low SWR on UHF band.
4 3 8 0 0.
Now all the test is completed. Building your own SWR meter is the best way to understand antenna system and RF power flow. And once you start measuring SWR yourself, you will never look at the antennas the same way again. If you enjoyed this video, don't forget to like, subscribe and share this video to your fellow radio amateurs. And let me know in the comments what ham radio project should be built next. I am Joman, Victor Uniform 3 India Zulu Delta 73 and thank you for watching this video.